All right, good afternoon, and thank you for being here. I hope you had a good Golden Week. So let me remind you what we have done last week, very briefly. I introduced the notion of indicator functions. These are very special random variables taking only two values, 0 and 1, and A is a subset of the set of events. And they have the special feature that the expectation of this random variable is equal to the probability of A. And this can be used for many purposes. Then I started with families of discrete valued random variables. I could do it, or I could introduce them as a vector, but for now I just consider n discrete valued random variables on the same probability space. And the first thing we have defined is a joint probability mass function. So this is a function which are indicated by p index x1 up to xn. It's a function from Rn to 0, 1, which is defined by when you take one point in Rn by this expression. So this function evaluated at x1 up to xn is just the probability that the points omega satisfy xj of omega is the value xj for all j between 1 and n. So it means you have n conditions. And it means also whenever these x1 up to xn are not in the range of the random variable x1 up to xn, this quantity is 0. In 2 dimensions, you can easily visualize this. You do a plot in xy, and at some points you put a probability and they have to sum up to 1. So I gave some properties of this function. You can also define a function of these n discrete valued random variables. You take any function g from Rn to R, no condition on g. And if you do this composition, so you can define g of x1 up to xn, it's a new function from omega to R. So it means it's a discrete valued random variable. You can compute its expectation with a formula which is famous. It's the lotus, and you can find it in the notes. A property of the expectation is also it's linear. You don't need any condition on x1 up to, here I wrote it x1 and x2, but this formula is true also if you add additional variables or random variables. It's linear, so you have this formula. Now I also introduce the notion of independent random variables. So if you have x1 up to xn, you say that they're independent if this joint probability mass function is a product. It's a product of the individual mass functions. And we have 2 small statements if the random variables are independent. The first one is the expectation of this product x1 up to xn. This is a very special function g, which is just a product of the variables. If the random variables are independent, this is equal to the product of the expectations. Be careful, there is no converse. So if you have such an equality, you cannot deduce that the random variables are independent. There is now a nice report on the website about this notion. You need more than this for going back to the independence. And if we have 2 random variables which are independent, there is a famous formula which is called the convolution formula, which says the probability mass function of this sum of x and y evaluated at one point can be obtained by this formula, and this is typically a convolution formula. And the last thing I introduce is this probability generating function. So this is a function defined on a small interval around 0 with value in R. In fact, we have shown that it's not such a small interval because this R, which is called the radius of convergence, is at least 1. Because we define it with this formula. So what is the definition? We sum over all, so this is for a discrete valued random variable. So then xj or xi are the values taken by the function, so it's only a countable number. We sum over I of this probability of x taking the value xi times the variable power I. This is a power series. And because these guys sum up to 1, we end up with the fact that this radius of convergence is at least 1. And the good point is this probability generating function contains all the information about these numbers. So when I say define uniquely the random variable, this is not completely true because it doesn't contain the value, or it contains it, but it's a bit implicit. But nevertheless, there is a one-to-one correspondence between such functions and the family of these numbers. So today we will start with an additional property of this function. So if you have any question in the room, you can ask me. If you have any question online, you can interrupt me at any time. All right. So we continue with this probability generating function. But before this, I need to introduce one more concept, which is a concept of moment. It's a generalization of the expectation. We are still in the framework of discrete valued random variables. So what is the definition of a moment? The first definition, so given discrete valued random variables x on a probability space, it's always the same. You have one probability space and a random variable on it, discrete valued. And given k is an integer. Given k, an integer, what we call the case moment of x is given by the expectation of x power k. This is a case moment. Of course, it doesn't always exist. So I have to add if it converges. Absolutely. Now we have seen this concept already a few times. It means when you write the formula, it has to converge with absolute values. In fact, if k is even, you don't need the absolute value because everything is positive, but for k odd, you need to put the absolute values. So this is a notion of the case moment. K is 1, you just get the expectation. And k is 2 is not very far from the variance that we have already introduced. So it's a generalization of both the expectation and the variance. So what is the link with the probability generating function? So we'll draw a link between this function and this case moment, but only for subfamily of random variables. So let me say what is a x is an integer value. It's an integer valued random variable. If xi is I. And in fact, we have seen already many examples. If you look back at section 2.2, when I introduced 4 examples, they were already of this type. The Bernoulli or the binomial or the geometric distributions are already, it's rather natural for application that you consider values which are just integers. So you observe these integers valued random variables, they belong to the set of discrete values because you have only a countable number of integers. So they are inside the set of discrete values. So we are just in a subfamily when this condition is satisfied. And we will see in a second why we need it. Otherwise, a certain formula has no meaning. So the link between probability generating function and this case moment is straightforward if you deal with integer valued random variables. And so one observation which I need before the statement, if you have already studied power series like this, maybe you remember that these functions are differentiable an infinite number of times as long as you stay inside the radius of convergence, and the derivative are just obtained by taking the derivative of these powers. So gxk, this notation is a case derivative of this function, is always well defined. On this interval minus RR, so on the radius of convergence. And if R is 1, then the question is, can I consider the limit as going to 1? So then the limit as going to 1 of this case derivative of the function can, or it depends, can not exist. So it depends on the function. There is no general statement. It's well defined inside the interval, just at the boundary, you cannot say. Except for k is equal to 1, of course, we know it exists because this is just 1. But for other k, we don't know. It depends. But I gave some example last week, so you can check on the examples of last week if it exists or not. So what is the relation I already mentioned between this probability generating function and these moments? So if x is integer valued, the specific class of random variables, then for any k integer, what we have, the limit when s goes to 1 of this case derivative. I'm relating this case derivative of this probability generating function to this expectation of x times x minus 1 times x minus k plus 1. If they exist. So please pay attention to the statement. I'm not claiming that it always exists. And we have seen at least one example where already the mean was, no, the expectation was not well defined. Okay, so I said something wrong before. The expectation does not always exist. We had seen one example last or 2 weeks ago where it doesn't exist. So it's not always sure. But the statement is, if both sides exist, then they are equal. That's the statement. And we are going to look at the proof because we can learn just a little bit. And when I wrote this, I had finally to decide what is n. I changed from one course to another one. So probably for this course, it starts at 1. It doesn't contain 0, because otherwise there is a problem with this statement. But it's not written in the notes. I haven't defined n in the notes so far. This is not a big issue. Simply depends what you do. Sometimes 0, it's convenient to have it inside. Sometimes it's annoying. That's the only thing. But already before I give the proof in particular, so let's apply this formula for k is 1. We observe that this gives us the limit when s goes to 1 of the derivative of this function. This is when k is 1, yes. And the second thing we can say, what about x squared? The trick is you can rewrite x squared as, you have to rewrite it like this. And just before I mentioned, whenever you have two random variables, the expectation is linear, so I can write this as the expectation of the first one plus the expectation of the second one. And now if I use this formula, we have that this is equal, if it exists, the limit when s goes to 1 of g second derivative plus g first derivative. So it means if these quantities exist, then if you know the probability generating function, you can compute these moments or these quantities. Or if you know these one, you can get an information about this function, but only at 1. What about the proof? And in the proof, we will see where we need this function, this random variable, to be integers valued. Proof is not difficult. So I start by computing this case derivative of this function. By definition, I need to take the derivative of this sum. I use a short notation. This pi I have already introduced is a probability that x takes a value xi. But in particular, in this case, it will be I. Remember, it is an integer valued function. This is a definition. So I need to take k derivative, and I will assume s smaller than 1, because for sure I'm inside the radius of convergence, because we know it's 1 or bigger. Okay, so I can differentiate, and I obtain the sum of I minus 1, I minus 2, up to I minus k plus 1 of pi I s I minus k. You just differentiate k times. There is only, it's a polynomial. And I'm going to keep, I didn't mention in the statement or before, this I is either all positive integers, or it's a subset if we have only a finite number of values. So, but for sure, I is a subset of n. Okay. And you could say, oh, I need to put a condition that this is bigger than k. Yes, but if you look, this will, if you keep it for all I in this interval or in this set, these terms will just cancel at the first k terms. So it's well defined. And okay, I call this gk of I. Together, yes. So I give a definition to this product. So I can write this as some of So I have just written the same thing. This should remind you something. This should remind you Lotus, which was for the computation of a function of a random variable. So if you look at Lotus, you had indeed the probability of x is equal to xi, and then a function of xi. But this is why, and this is where, here I don't have a function of xi, I have a function of I. And this is where it's important that xi is I, and this is why if you want to use Lotus, you need this xi to be I, and so you need an integer valued random variable. So you can just write this as O. So it's really Lotus applied to this specific integer valued random variable. This is nothing but the expectation of the function gk of the random variable x times s power x. No, s minus. Yeah. If you're not sure, go in the reverse direction. Write this with Lotus, and you will, in the special case of an integer valued random variable, and you will end up with this formula. So what we have obtained a formula for this case derivative of the probability generating function. And now, a bit formally, I will take the limit. Take limit s going to 1 of this equality. So what we obtain, limit when s goes to 1 of this, it was one side of my statement. It's equal to limit when s goes to 1 of the other side. And what you observe, please formally, if you can exchange your expectation of a limit, when s is 1, this term disappears. This is the expectation of this function of x. And this function of x is precisely the one I had written in the statement. X minus 1 up to x minus k plus 1. The only place, so the statement, if this limit exists, it's equal to this one, which is what I had written. Where you need to be a bit careful is this part. It can be done rigorously if you do it, if you write exactly what means this limit exists. And we are in a good setting. So there is no big problem. So if we summarize for very specific random variables, the integer valued one, we have a formula which relates the derivative of this probability genetic function to this expression, which is a bit complicated. But as we can see on this example, you can still use it in order to obtain the information about the moments.
Professor?
Yes.
In this calculation, we treat x, which is a random variable, and I, which is an index, and you seem to be treating I at the very end as a random variable, even though x equals I is just like a special case of that picking one value.
Yeah.
At the very end, when you say expectation of x, x minus 1, that x has to be a function.
I mean, I perfectly agree. I'm using this information. I'm using that it is integer valued. Otherwise, I cannot go from here to here. But if you use this assumption and if you check what is the meaning of Lotus, you get exactly this for this integer valued random variable. So this is correct. So I agree. There is one condition, but I mentioned it from the very beginning. And please check that. Maybe you should check the meaning of this on the 4 examples I introduced last week or 2 weeks ago, which are precisely integer valued random variables. And for them, for at least one of the, no, for 2 of them, this I is a finite subset. So you have only a finite number of coefficients which are not 0. And for 2 examples, it's an infinite set, but the thing is the same. So no, I agree, it's a bit confusing, but that's it. Any more questions?
So does that imply that from the start, I was a random variable?
No, I'm saying the random variable takes the values 1, 2, 3, and not 1.5, 2.3, and so on. It takes only integers value. But again, look at the 4 examples of section 2.2. This happens for some random variables. That's it. Okay, let me finish with this subject. Another use of this probability generating function for independent random variables. If x and y are independent, oh, okay, sorry. Before this statement, I should just add one comment. Sorry. I keep it here, but I need new interpretation of the generating function. So if you look carefully at this expression, as we just recall, this is a sum on I. Now we are in the integer valued case, so I can even write I in the range of x, Si, then this is a Px of I, or I can write it as P of x is equal to I. I just state the same thing. Observe that this is, again with Lotus. When you look at Lotus, for an arbitrary random variable, it would be xi. And here we would have a function of xi. But now xi is I. So if I apply Lotus, I have simply s power x. So it means this function can also be seen as the expectation of, it's a composition of 2 functions, s power x. And this will be useful in the next statement because we know some properties of this function. So if x and y are independent integer valued random variable, then the statement is that this function g of x plus y evaluated at s is nothing but the product of these 2 probability generating functions. And the claim is that this is very easy to prove. So let's check. Once we have what is on the right, because look, gx plus y evaluated at s is nothing but the expectation of s power x plus y. Now this is with this interpretation. Oh, maybe you could complain, but it's true. The sum of two random variables which are integer valued is still integer valued. Otherwise, I couldn't do it. Maybe I will add this in the note. Because it takes both take only integer values, so the sum is still an integer value. So I can write this. Now, you should not be scared. I agree these are random variables, but it's just function on a certain space. And we know a property of something power x plus y. This is expectation of s x s y. Now, by assumption, these two random variables are independent. So one property of independence is precisely the expectation of the one function of x, a function of y is the expectation of the first one times the expectation of the second one. I mentioned this in the notes. And now I just come back. This expectation of the first one is this probability generating function of the first random variable times the probability generating function of the second one. That's it. So probably if we don't use this interpretation, it's a bit more complicated. Again, if you have any question, interrupt me. And then we are going to look at a quite specific example, but we can learn something. So I decided to keep this example. It's about product of n independent integer valued random variables, but with an n which is random itself. So product of n integer valued random variables. And they are independent. But when n is random, and you can find some examples. This is a classical example, so you can find an application when this takes place. So what is the statement about this situation? So I need to define for I any number, xi and n. So now capital N is going to be a random variable. Xi and n are independent. And integer valued random variables. And I will assume that all these xi follow the same probability distribution, or they share the same, they are the same. So let's say with all xi following or let's say identically distributed. So it means, for example, they are all Bernoulli random variables or all random variables of a certain type. They are all the same. So it means you repeat and all xi, you repeat n times the same experiment with the same outcome. So we have a certain number of random variables, integer valued, and another new integer valued random variable. They are all independent, and all xi are identically distributed. Okay. Now I'm going to, and since they are all identically distributed, I will use just a natural name following. So they follow a certain distribution following a random variable x with generating function. With generating function jx. Set. I have a small problem with notation because I'm going to have too many s, so I use a capital S. I do a sum of n of them, but as I said, the number is not known. So this is why this index is this integer valued random variable. I do this sum with an unknown number of copies of this x1 up to xn. And the statement is its probability mass function. Not probability generating function. Its probability generating function satisfies. So it means I'm going to compute G, this S evaluated at S. So be careful, this is not the same. This is just a small s, which is a variable. This guy is the generating function n of Gx. This is a statement. So what does it mean? It means this, we will record what it is, but it's a probability generating function for this random variable is given by this generating function. It's a function on the value of this. So it's perfectly meaningful as a composition of functions. And I decided to show it because the proof, we can learn something from the proof. We can learn how to make such a proof. It's interesting. So again, if I want to prove this, I take s smaller than 1, because I know that for s smaller than 1, everything is well defined. And I define what is Gs of S. By definition, or by what we observe, this is expectation of small s power is capital S. This is what I introduced before, which is the expectation of S x1 plus x2 plus up to xn, which is not known. And now we are going to use what we have already introduced, a partition theorem. Partition theorem for expectation. I will write it on. So this is the sum. It's a sum over n from 1 up to infinity. Okay, this was the theorem I mentioned for the special case of this partition theorem for expectation. it's, you assume, so it's a sum because it's a partition, so all subsets are disjoint, so it's a sum over small n from 1 up to infinity. You assume that, oh, sorry, it's not xn, this is n. You assume that this random variable takes a value, I hope in the note there it's not a mistake, it should be n here. You assume that n takes a value n, small n, and you make times the probability that this condition holds, right? And now, if with this formula, I can simplify because inside this expression, I know that this capital N takes a value small n. So it means I can write this as a sum n from 1 up to infinity of this expectation, this conditional expectation of Sx1 up to a finite xn times the probability that n takes the value n. And now, what we said before, oh, this I can use a property of this exponential. So I end up with some n1 up to infinity expected. It is Sx1, Sx2, Sxn. And now I use the independence. For the independence, you can try this as a product of expectation. But the expectation of all these guys are the same because I have assumed that they all follow the same distribution. So it means I end, yes.
Is the sum from 1 to infinity? Shouldn't the sum be finite? Because we know there's a finite number of.
No, n, precisely, n I don't know. It can
But we don't need to sum from n equals, simple n equals 1 to infinity, right? We can go from simple n equals 1 to capital N.
No, be careful, capital N is a random variable.
Oh,
so
okay.
It wouldn't be meaningful to put a capital N here. No, it's correct. But now I'm using the fact that they are independent and all equally distributed. So you have n times the same thing. So let me write, we have still this sum n from 1 up to infinity. We have this expectation of Sx, and instead of writing n terms which are the same, I just put a power n times probability of n is equal to n. And now I need to think, what is this expression? This is nothing but gxs power n. What I mentioned before. And now I'm again going to use Lotus. This times the function is equal to gn of gx of s. It's always easier, start with this, and if you expand, you're going to write to get the previous line. And this is what I stated. This is equality. So you can wonder, is it really simpler? The answer is yes. Why? Because first, it's very close, so it's a closed formula. But in addition, it's easy to compute something from this. I encourage somebody to write a report about application. It's very famous, so you will find in one application in all textbook. So what is this? What is the expectation of S, you can wonder what is this expectation for a random sum of integer valued and identically distributed and independent random variables. We are going to use what we have seen just before. So I'm going to compute this. What is the derivative of this function? For s smaller than 1, I can always do it. It's a composition of two functions. That needs derivative of a composition. So derivative of a composition, this is derivative of the first one evaluated at the second one times the derivative of the second one. Okay. And now, if I want to compute the expectation, I need to take the limit when s goes to 1. So if it exists, if I can take this limit, and of course this depends on x and on capital N. If we can take limit s goes to 1, one gets the expectation of this, because the left-hand side converges to the expectation of this, is equal to, so I take the limit, it makes gn prime at gn gx. This is formally what I get. And now you just need to remember what is this. This is 1. We have seen it last week. So it means this is g prime n at 1 times gx prime at 1. And by definition, this is the expectation of n times the expectation of x. So you get that the expectation of this random sum is a product of the two expectations.
Excuse me.
Yes.
And right hand at the right in the blackboard.
Yes.
G prime x.
Yes. Thank you.
Thank you.
Yeah. Thank you, Kato-san. It's good to have a PhD student. No, a PhD holder in the class. All right. No, it was a x. It's an internal derivative. Yes. Of course, again, assuming that these expressions exist, I'm sure you can find an example where it does not. It depends how these converge, and the same for x. But let's assume we are in a good situation. So we have seen some applications of this probability generating function. And this is a common notion. It appears in different fields. In statistical mechanics, you also have these kind of functions. Any question or remark?
One more question about the middle board. So for capital S, not capital S, but the S with 2 lines to be a random variable, it needs to take a discrete set of values from R, right? We said something like it has to have a discrete mapping. But if you're mapping from n equals 1 to infinity, that is not is that a discrete mapping? Because it's not a finite subset of R.
No, it is fine. These ones are integer valued. So they take only integers numbers, and an arbitrary sum of integers is still an integer. That's it. You cannot leave the set of integers. So no, we are still in the framework of integers valued random variables. That's correct.
Okay, thank you.
Okay, so that's it for chapter 2. It was a rather long chapter. It's all about integer valued random variables. If we summarize why it's so simple, it's simple because the range is countable. So when you take a function of such a random variable, you don't have to impose any condition on G. We have seen. The new chapter is more general. It contains the previous ones, but it's good to separate the two subjects. So this chapter 3 is random variable. Or I should, yeah, random variable. But the general case. Well, general case. So it means I will drop this assumption about integer valued or countable image or discrete value. Just already pay attention with this new one, and it will appear usually. The probability of x equal to x is going to be 0. Not always, but it's going to be 0 most of the time, we will see. Which means the probability mass function will not be very useful. I need to change the concept. I will come back to this, but yeah, pay attention. Usually 1 point is going to be meaningless. So we shall consider instead, the probability that x is smaller or equal to a certain value. This is going to be more meaningful because here you have a half line. So this is the same as probability that x belongs to the half line minus infinity x. And of course, it will in general not be 0. But we will see. So I will start with univariate random variables, which I already mentioned briefly at the beginning of chapter 2. What means univariate? It means they take range in R. They are one-dimensional in this sense. Later, we will see random vectors, which means function taking value in Rn, and they are useful. So for now, I take variables in R. So what is the definition? On probability space, univariate random variable. X, I keep the same letter. It goes from omega to R. Or, no, the sentence is not good. So it is measurable. I will have to explain function from omega to R. So there is one word which is not defined yet, but it means it's going to be one random variable, one function from omega to R. As before, you can see I don't have any assumption about the fact that the range is discrete or countable, but I have this word measurable because I need to say something. What means here measurable? It means x minus 1 of minus infinity x belong to F, or equivalently, the set of small omega in omega, such that x of omega is in minus infinity x, this set is in for any x. This is the notion of measurability. And it's natural that I need to say something, because look, when I wrote this, if this set is, if x does not satisfy this condition, this is simply not meaningful. I can measure, I can give a probability only to set in F. So it means if this set is not in F, I cannot give a weight to it. So you can do other things, but I cannot speak about the probability of this set, so it means I could not write this. So this is a new condition. A function is measurable if the prime, this is called the preimage of this interval is an interesting event. And by the way, you can check this is equivalent to x minus 1 of minus infinity x open within F. I decided to choose a closed interval, but it's the same if you take only open intervals. And for this, in fact, for discrete valued, we had already this, but for discrete valued, this is only true for discrete value, the last line. This is still equivalent to preimage of just one point is in F. So it means for discrete values, you have more choice. You can decide either, and for sure this was meaningful otherwise. Again, I couldn't write this. So all the theory I have presented would be empty if I cannot write this, because everything was based on this for discrete valued. But it's the same as saying that this interval is in F or that this interval is in F. But yeah, this last line is only for discrete valued. So I need something. This is part of the analysis. But you observe once again, I have no condition about the range of X. I'm not saying that the range is discrete or whatever. So I need to replace the probability mass function, because the one point usually has no meaning or has a weight 0. We need to replace. It was a probability mass function by something more useful. Still, the PMF is useful if you are dealing with discrete valued, but in the general case, we need something different. Definition. So given X univariate, I will not always write this anymore, but just the first time. Univariate random variable on a probability space. Maybe I should also, before I finish, I'm claiming that, I want to claim that you are in fact familiar with this kind of random variables. If you think about the position of this point in space, you cannot precisely say that it is exactly here. So one value, which means exactly at this point in R3, is usually, if you do any measurement, it's probably not meaningful. You need to say, oh, it is in a small box, maybe very precise, but you can only say, my measurement experiment tells me it is in a small box of this size. So I cannot write P, the probability of having this point exactly at X. On the other hand, it's usually meaningless. On the other hand, I can write the probability that my point is in a small box. I just denote by B a small box. So this is a natural concept when you have a continuum. So I can finish this. So given a univariate random variable on a probability space, the cumulative distribution function, cumulative distribution function, which is abbreviated as CDF, you can almost guess the end of the sentence. Because with what I have introduced, there is not so many choices. So this cumulative distribution function, which has a name, it's called fx, is defined by so first, this function, it's a function on omega with value, no. It's a function on R. A function on R with value in 0, 1, 0, 1. And how we define it? For x, any number, by fx at small x is simply the probability of x smaller or equal to x, which is the same as this measure of the set of omega, so that x of omega is smaller or equal to x. I said you can guess it because this is the only thing I have introduced in my theory so far. I can measure these sets. So I define a function, and we will see these functions are very special, which does give me the probability that the random variable takes a value smaller than or equal to x. Why I'm claiming that this is quite common. So it's a function defined on R. There, I'm claiming that there are all of these type, more or less. Here. And it is first, they are increasing. Why? Look, so observation. There are 4 observations, 3 of them are trivial. 3 of them are trivial. First, increasing. Now you should be familiar with this. Why? Because if you take 2x, 1x and 1x prime, of course, one has to be bigger than the other one. These sets, one is included into the other one because you have, if x prime is bigger than x, then minus infinity x is included in minus infinity x prime. And the probability of the first one is, of course, smaller or equal to the probability of the second one. So it's increasing. This is the first observation. Limit fx at x when x goes to minus infinity. It has to go to 0. It's rather intuitive. If you want to prove it, it's not difficult. Now the limit when x goes to 1. No, x goes to infinity. X goes to infinity of this guy is 1. because you take everything. And on this picture, I paid attention of doing it right continuous. So if you have a jump, of course, if you have a jump, you have to decide if the function takes the value here or here. And the claim is if you have a jump, the function has to take the value on the right, which says fx is what we call right continuous. And I will write more precisely what it means. And we will prove it because, again, we can learn something. Usually I give proofs when we can learn something from them, which means the limit when epsilon goes to 0, f of x plus epsilon is equal to f. It means when you approach x from the right, you get the value at x. On the other hand, I'm not claiming that if you approach from the left, you get the value. You would get the value if the function is continuous at this point. But if you have a jump, precisely this wouldn't be true if you put a minus. Is it clear, the notion of right continuity? How to prove it? And before I gave the proof, you can wonder why it's asymmetric, why we have right continuity and not left continuity. The key point is here. We are taking something smaller or equal, and the equality is included. We will see that it's because of this that we have right continuity. If you take a strictly, I didn't check, but I suspect that if you take a strictly smaller, you would have left continuity. You can check, I think so. Yes, probably. Okay, so let's give a proof of this, because it's based on things we have seen. It's not completely trivial, but still it's understandable. So the proof for the last one, I'm going to consider a family of sets. Set AN, it is the set of omega, such that our x is fixed. Yeah, already here for any x fixed. So I take AN, a subset of the set of omega, such that the function x take value bigger than x plus 1 over n, and n is an integer, not 0. So first we observe what is the complement. The complement is a set of omega, so that x of omega is smaller or equal to x plus 1 over n. This, by definition, is an element of f. Remember, x is measurable, so everything smaller than a certain number is measurable, which means by complement that AN is also in f. It's also an interesting set. It's an interesting event. So this is the first thing. And the second observation is an inclusion. AN is included into AN plus 1. Check what is bigger than, if you have an n plus 1, 1 over n plus 1 is smaller than 1 over n. So it means this inequality. All right, I need this information. And now, what is a union what is the union over n of an? That's, you want the set of points which are bigger than x, the union, x plus 1 over n, but n is arbitrary. I'm claiming this is a set of omega such that x of omega is strictly bigger than x. Yes. Think about it. This is true because to a picture you have x, take a 1 over x plus 1 over n, x plus 1 over n. When n becomes bigger, you are always taking this part. So if you fix any point here, take n sufficiently large and you can cover it. That's the idea. So we have this union is a countable union of an. So I have everything now. I can go on with the proof. So what I have to compute, I want to compute limit when epsilon goes to 0, fx of x plus epsilon. First, this is a small observation. I can replace this by, be careful, you cannot always do it. Think about a very nasty function. If you take a very nasty function oscillating a lot, you cannot always say that the limit when epsilon goes to 0 is obtained by just taking those 1 over n. But the function is increasing, or yeah, it's increasing. So you don't have oscillation like this. So you can do it with an epsilon argument. You can replace this limit by just looking at some points, which is, this requirement seems weaker than this one, because here you take all points up to a certain size. Here you just look at some. So, but still, because the function is increasing, it's the same. Yes. Okay, so let me write what it is. By definition, this is a limit n goes to infinity. What is this? This is probability of x smaller or equal to x plus 1 over n, right? This is a definition of this function, f. And now I use something that we have seen about continuity of probabilities. When you are in this setting, you can rewrite this as limit n goes to infinity of, no, there is one more step. This is P of an complement first. It's still written here. This is a complement. And now, no, what I think. Complement is 1 minus the limit n goes to infinity P of an. Because the complement is of size 1 minus. And now I'm going to use this assumption, because now we are dealing with an. It's in chapter 1, probably. This is 1 minus the limit n goes to infinity of the probability of the union of an. There is even probably a report on this. So you can transform this limit with probability and the union. This is a theorem of chapter 1. The continuity of probability. And now, oh, what is this union? It's this. Okay, so I need more space. So this is 1 minus the probability, 1 minus the probability that x here, this was a unit, x is bigger than small x. But now take the complement. This is the probability that x is smaller or equal to x. And this is nothing but px, fx of this. So what we use the property about complement when you go from one set to its complement. I mean, the sum of these two probabilities. One, we use a result of chapter 1 about continuity, and this observation. So yeah, we have used several things that we have already seen. But it means, if you look at the starting point, we have shown that it's right continuous because the limit from the right is equal to the value of the function at this point. Any question?
No, not from the limit. I guess.
Oh, in fact, sorry, you are right. No, this is probably a mistake. There is no more limit here. I hope I haven't done this mistake in the note. Sorry, it's in my notes. I don't know in the lecture notes. Please check. Is it correct in the lecture notes? Okay, so it's here. Sorry. Yeah, this is the result we have seen in the notes. This limit of, because they are, if you're not sure, you need to do a picture, but look at these pictures, they're all included into one another, and you get this. Yeah. There is a limit, so it's a mistake. So I will correct it. But maybe okay. Usually I correct some typos whenever I found, but I'm not sure I corrected this one. So you have to upload always the most recent version. Okay. Now, just one remark. I will not develop this, but you remember the PMF, and we had seen these, for example, in section 2.2. From a probability mass function, we can reconstruct a probability space and a random variable. So whenever you have a function which takes values on a countable set and sum up to 1, we can reconstruct a probability space, a random variable, and so on. Here we can do the same. Is given a function, and I just call it capital F from R to 0, 1, satisfying the 4 properties I just mentioned. So it's increasing its limit at minus infinity 0, its limit at infinity is 1, and it's right continuous. So if you take a function satisfying these 4 properties, they exist. There exists a probability space and a random variable. So it means a function which is measurable such that the cumulative distribution function is equal to your initial F. Usually this construction is not so useful, but it's good to know that you can do it. It's similar. Now, an observation. You can, I mentioned already a small box, so let's take an interval. If I compute the probability that A is strictly smaller than X, smaller or equal to B. A and B are real, and of course I assume that A is smaller than B. So please observe that this is the same as the probability of X smaller or equal to B minus the probability of X smaller or equal to A. Take the interval AB, this is the same as, so it's an open interval here, a closed interval here. It's the same as everything minus this. And I can express this in terms of fx of B minus fx at A. So this cumulative distribution function is also useful just for getting an information about the probability of having X in a certain interval. However, please pay attention. I took it strict here and non-strict on one side because in general, it is not equal to the probability that A is smaller or equal to X, smaller or equal to B. There is no reason why these two things should be equal. In particular, they are not equal if P of X is equal to A is not 0. So one point can be important. If the point A has a certain probability which is not 0, just the point A, then these two quantities are not equal, because if you include A in this interval or if you exclude it, and if A has a certain weight, they are not equal, right? So you would like to say or when these two quantities are equal or not. So there is a definition which is natural, and you will see why I'm doing this definition. Random variable. A random variable X on a probability space is continuous if precisely the probability of one point is always 0. So I say it's continuous if the probability of one point is 0 for any X, which means you can directly observe discrete valued random variables. I will use a strange notation, but we will give a meaning to it later. Yeah. They are orthogonal in this, it's not precise yet, in the sense that no discrete valued random variable is continuous, because you would have a contradiction, and no continuous is discrete valued. So these are two kinds of sets which are very different. Two kinds of random variables which are very different. There are two extremes case. This one has only discrete values, so only points matters. This one, the continuous one, points do not matter. And we will see that, in fact, this is at the root of one theorem, which is Lebesgue decomposition theorem. We will mention it next week, probably. So I have introduced continuous random variable, and of course, for continuous one, we have this equality. For continuous random variables, you can write without any problem the probability of A smaller than X smaller than B is the same as the probability A smaller equal to X smaller equal to B. And you can also write A. In fact, you can deduce the last two, but from the other two. Okay, so you can, if it is continuous, you have no problem of this type. And by definition, 1 point is not important. Okay, last thing, and we will finish with
Professor?
this. Yes.
There are only continuous and discrete valued, right? There's no third type.
No, oh yeah, you're right. There is only continuous or discrete plus linear combination. You can make, you can take a linear combination of continuous, not arbitrary linear combination. Be careful because you still need to have some, I mean, the probability of the entire set has to be 1. But yeah, you have combination of continuous and discrete valued. But then continuous, wait a second, continuous will be divided into 2 parts. Continuous, we will introduce and study the absolutely continuous, and there is a second part which is singularly continuous. We will mention it because it's part of the story. One more question or remark?
Yeah, but the definition of continuous says probability x equals 0 for all x in R. So if there's some linear combination, then the domain of x should not be for all x.
Read what is on the blackboard. I said that discrete valued for now has 0 intersection with continuous. I do not mention now anything which is a kind of linear combination. In the general definition of random variable, we can have, okay, one exercise for you, construct an explicit example of a okay, given meaning to this picture. This is a probability, a cumulative probability function of one random variable which is neither discrete valued nor continuous. Because at this point, I'm claiming that it has a jump. So it means the point here is going to have a certain weight. On the other hand, on this part and on this part, it's going to be continuous. So I'm claiming, but this vague statement here is that if I have only lines, it's continuous. If I have only dots, it's discrete valued. And it turned out you can make things which are a kind of linear combination of both. But I haven't, I mean, it's included in the theory. I haven't just not mentioned what is linear combination. It's just this. Or if you want to do, no, it's misleading. Because as you can see, you cannot do arbitrary things. I mean, I still need this cumulative distribution function to sum up to 1. So I cannot just take a continuous one and a discrete one and do arbitrary things. I need to be a bit careful. All right, so I will not start the next question, but you can wonder, what about function of a random variable in the general setting? Remember, when it was discrete valued, I had no condition on G. But now, if I want this to be a random variable, I need it to be measurable in the sense given. So it means Gx -1 of any interval like this has to belong to F. So if you know it for X, how can you ensure, what condition on G ensure that you have this? Which is a bit technical. I will not spend so much time, but you can guess it's not true for arbitrary function. I need to do something. So I will just mention this next time. And then I will start with a subfamily of continuous, which are the absolutely continuous because they are the most important one. Nevertheless, I will mention, I would be happy if somebody find an example, a concrete example of a singular continuous one, but I will mention this next week. Okay, that's all for today. Thank you.